Hey everybody, this is part 3 of the 4 things to know about the gradient. Now, we're actually still just on the second thing to know about the gradient, which is its relationship with directional derivatives. But I wanted to do a quick derivation of the directional derivative using the limit definition and using what we know about linearizations. I put the definition of directional derivative up. You'll remember from the book that the directional derivative at p in the direction u, where u is a unit vector, is the limit of this difference quotient as h goes to 0. Now, to give a little bit of background on why this formula makes sense, let's take a look at the direction in which we're going. This is u, in this case, negative 3 over root 10 I plus 1 over root 10 j. That's telling us which way we're going. And I've broken that up into components. U sub 1 is the x component, and u sub 2 is the y component. So what this formula is saying here is I'm going to measure the value of f at a point that is a little ways out from the point AB in this direction. So what I've done is I've taken HU, which is equal to HU1I plus HU2J, because U is equal to U1I plus U2J. And I've moved out that much from the point A comma B, and I've taken the value of f there. I subtract the value of f at the point P so that I have a difference of values of f, that is a change in f. That's my numerator. My denominator just tells me how far I went. Because I moved along the vector h times u is a unit vector, so its length is 1, which means if I multiply it by h, the distance that I've gone is h. Okay, so again, this is just a rise over run. It's just written this time in an algebraic form. Now let's see what shakes out from this formula if I try calculating the limit. That is, if I try simplifying this expression here. Now the way I'm about to do this involves just a little bit of hand waving still, because I'm using the linearization as an approximation for this value here. There is a way of doing this so that you're not doing the hand waving, but I don't think it's much more informative than what I'm about to do, so I'm just going to do the hand wavy version. What I have here is, again, a change in f. That is, it's a delta f. I'm going to write that down in shorthand, delta f over h. And then I'm going to use local linearization to rewrite what that change in f actually is. That change in f is approximately f sub x times the change in x plus f sub y times the change in y. But I have the changes in x and y. Those are recorded here. The change in x was from a to a plus hu1, so the change in x was just hu1. So I have f sub x times hu1. And similarly, my change in y was hu2. And I'm dividing all of this by h, that is the run. Okay? And now I'm out of room on the board, which is typical for this situation. So I'm going to rewrite this up here. Let's see. No, actually, yeah, I think this is really the only place I can reasonably go with this. So now I have the limit as h goes to 0 of f sub x u1 plus f sub y u2. You'll notice this expression has no h's in it, which means taking the limit as h goes to 0 now is trivial. This is just equal to f sub x u1 plus f sub y u2. And that's equal to, again, the gradient of f at p, which gives me my f sub x and my f sub y, dotted with the vector u1i plus u2j. That's just the vector u. So again, I see that the directional derivative in the direction u of f at the point P is the dot product of the gradient of f at that point and the unit vector that tells me what direction to go. Okay, so that's a slightly more formal, still not totally formal, but a little bit more formal explanation of how this dot product relates to this expression here. the main thing to keep in mind is that this difference can be approximated using local linearization, which is exactly what I did here. Oh, and I've lost it because I had to erase. That's terrible board work on my part. But if you go back in the video, you'll see that the local linearization contained in itself a dot product of the gradient with something else, and that something else was a vector telling me where I went. Okay, so just to summarize, this equation right here, this formula, that's the second thing to know about the gradient. The gradient is super useful for finding directional derivatives. That, by the way, is why we wanted to turn the partial derivatives into a vector, because it turned out that that expression I came up with for the difference in values of f, that expression really contained a dot product with the vector f sub x times I plus f sub y times j. That vector is naturally contained in that formula. So, just to summarize, the reason we write this gradient as a vector with the partial derivatives as coefficients is because that allows us to relate directional derivatives to dot products of gradients with certain direction vectors. Okay, so that's the second thing to know about the gradient. And for practical purposes, when finding directional derivatives, you're usually going to use this formula. Trying to use this limit definition is clunky, and as you found out while doing the prep assignment last week, trying to estimate it from a picture is clunky, although you can get a good idea whether it's positive or negative. And by the way, many of you got very accurate estimates, so I wouldn't knock what you did there. But you'll find that usually this is the most convenient way to find the directional derivative in a given direction. Okay, so that's the second thing to know about the gradient. In the next video, I will give you the third and fourth things to know. Actually, sorry about that sudden cut there, but there was one more thing I realized I really needed to emphasize about finding directional derivatives that students always forget, and it's a natural thing to forget if you don't really understand where things are coming from. You'll notice when I did this calculation here, I assumed that my direction vector u was a unit vector, and I know I said that before, but I think it deserves saying again. When finding directional derivatives, you must always assume that the direction you're going in is given by a unit vector. And I want to say a little bit more about why in this calculation that was important. Because if the calculation works no matter whether the direction vector is a unit or not, then I shouldn't have to assume that. But there was a specific place in this calculation where I assumed that u is a unit vector. And that place was when I was talking about this denominator here. This denominator h is a measure of how far I went. But that is only true if u is a unit vector, because the vector that I traveled along was hu, which was hu1 I plus hu2 j. Now this denominator should be a measure of how far I went. Okay, so this should be the magnitude of hu. But assuming that h is positive, which I can assume here, that magnitude is going to be h times the magnitude of u. The magnitude of u is 1. So the magnitude of h times u, that is the distance that I went, is h times 1, or h. That's why this denominator is allowed to be an h here. That's how that relates to what's going on up here. Okay, so just keep in mind, when finding directional derivatives, it's very important to make sure that the direction vector you're using, your u, actually is a unit vector. If it isn't, you should do the operation that I did in the last video, which is find the magnitude and divide that entire vector by that magnitude to get a unit vector. Okay, so I realize that's really just a re-permutation of what I said earlier, but I wanted to make sure that I had proper emphasis on it. Okay, stay tuned for the next video.